Hello, this is Dr. Habib Ahmed, and today I'm going to show you how the latest technology works with the help of Silvaco TCAD simulation. First, I'm going to show you how to perform the Silvaco TCAD simulation of a short channel 45 nanometers gate length CMOS inverter. And secondly, I'm going to show you how to perform the Silvaco TCAD simulation of a 1 micrometer long channel CMOS inverter. With that goal in mind, let us first talk about a few basics of CMOS and the CMOS inverter, and then later we will switch to the Silvaco TCAD simulation of short channel and long channel CMOS inverter. CMOS stands for complementary metal oxide semiconductor. CMOS technology is a fundamental building block of modern integrated circuits and microprocessors. CMOS technology uses complementary pairs of metal oxide semiconductor field effect transistors. These transistors are N-channel MOSFET and P-channel MOSFET. The combination of N-channel MOSFET and P-channel MOSFET transistors are fabricated on a single substrate, typically silicon, and they are widely used in digital circuits, memory chips, microprocessors, and other semiconductor devices. So basically, here we are looking at just two transistors fabricated on a single substrate, but on actual devices, for example, microprocessors and memory chips, there are billions and billions of transistors fabricated on a single chip. The way it works is that the NMOS and PMOS transistors work together in a complementary fashion, where one type is on while the other type is off, reducing power consumption and heat dissipation compared to other transistor technology. So, one of the significant advantages of CMOS technology is its low static power consumption, and this is because CMOS consumes power only when switching between states from 0 to 1 and 1 to 0, or logic low to high and logic high to logic low, unlike other technologies that can draw continuous power. So here let us look at slight details of this structure. Forget about the substrate connection, this part, and this connection over here as well. So basically, assume that our starting material is a p-type substrate, and we want to fabricate an NMOS or N-type MOSFET. For an N-type MOSFET, the substrate is going to be p-type and the channel should be N-type. So the drain and source should be N-type. Similarly, we have a field oxide, a gate oxide, and then we have a polysilicon gate or a metal gate, where polysilicon gate is preferred due to several fabrication reasons. Now, this constructs an N-type MOSFET. Let us talk about the P-type MOSFET as well. In order to create a P-type MOSFET on the same substrate, the first thing we need to do is to create an N-well. This well acts as a substrate for the P-type MOSFET. In a P-type MOSFET, the substrate should be N-type and the drain and source should be P-type, because we need to create a channel which should be comprised of holes under the gate. And then there are a lot of fabrication steps involved in the manufacturing of this complementary metal oxide semiconductor. I'm not going to go into the details of that. We will leave it for another time, for another lecture. Let me ask you a question. Have you ever thought that with every new generation of our phones, the functionality is improving, like the processing speed and the memory size of our phones is improving. However, the size of the smartphone remains the same. Like the first generation iPhone was introduced in 2007. iPhone 4 was introduced in 2010. iPhone 6 was released in 2014. 8 was released in 2017. iPhone 12 was released in 2020. And iPhone 13 was released in 2021. And every new generation of these smartphones has better functionalities as compared to the previous technologies. They have higher processing speeds and higher memory sizes and other functionalities as well. Now, have you ever thought, how come the size of the phone remains the same, however its functionality is improving? Now, to answer that question, let us scroll down the slides, and the answer to this question is Moore's law. So Gordon Moore in 1965, with the help of 45 data points, predicted that the number of transistors on the same size chip doubles once every 2 years. And this trend has been continuing until now. Scientists and engineers, they are trying their level best to keep up the same trend, that is to increase the number of transistors once, or double the number of transistors on the same size chip once every 2 years. But how does it happen? So, in order to answer that, let us look at this structure, which is a CMOS inverter structure that I designed using Silvaco TCAD. And in this structure, here is the doping profile. Here is the drain and source of the NMOS, and this distance between the drain and the source is called the channel length, or we can also call it technology node. So assume that this transistor has this channel length, and then its width is kind of inverse. In Silvaco TCAD, in my simulations, I generally keep the width of the structures to 1 micrometer, which is the built-in width for, or the z dimension of the structures in Silvaco TCAD. So, if I with the new, for the new generation, if I reduce each and assume that this transistor is in square shape. So if I reduce the dimension of this transistor by 0.7 times, so I reduce this side by 0.7 and the inverse side as well by 0.7 times, 0.7 into 0.7 comes out to be 0.49 or approximately 0.5, which means that I have reduced the area of this transistor by approximately half. If I reduce the channel length by 0.7 times and the width as well, I almost reduce the area of this transistor by half. And if I reduce the area of the transistor by half, it means that now I can fit double the number of transistors as compared to the previous technology. And that is what has been happening over the years. We try to shrink the channel length by 0.7 times so that we can double the number of transistors and we can double the functionality of the smartphone and processors and memory chips at the same cost, because it's taking us the same area. While there are other complicated features involved, like the cost of the mask increases if we keep reducing the dimensions, but anyhow. So with almost the same price, we can double the functionality of our electronics. And that is what has been happening so far. Now, let us move to, let me close this one. Now, Let us talk about the CMOS inverter. Why are we interested in the CMOS inverter? The CMOS inverter is a fundamental building block in CMOS technology. The primary function of a CMOS inverter is to invert the input signal. When the input is high, the output is low, and vice versa. And this inversion capability is essential for logic operations in digital circuits. So for example, here is a circuit diagram which kind of is similar to this structure that I have made. I'm going to place them side by side so that you can better view them. In a CMOS inverter, we have a PMOS transistor and an NMOS transistor. Their gates are connected together. So like over here, what I have done in this Silvaco TCAD simulation, here is the gate of the PMOS and here is the gate of the NMOS, and I've connected them together. Similarly, the drains of the PMOS and NMOS are connected together. And this is what I have done in this structure as well. Here is the drain of the PMOS and here is the drain of the NMOS, and I've connected them together. The source of the PMOS is connected to the supply voltage. Here is the source of the PMOS, and the source of the NMOS is connected to ground. Here is the source of the NMOS. If the input is high, the NMOS is conducting and the PMOS is turned off. So since this transistor is conducting, the output would be connected to ground. So if the input is high, the output is gonna be low. Similarly, if the input is low, this PMOS is conducting and the NMOS would be turned off. If the PMOS is conducting, the output would be connected to the supply voltage. So if the input is low, the output is going to be high. Now, I also told you that we will discuss the Silvaco TCAD simulation of a 1 micrometer CMOS inverter. Anything around 1 micrometer or above channel length is considered a long channel device, and anything around 100 nanometers or below, you can consider it, or even slightly like something way lower than 1 micrometer is considered a short channel device. Particularly if we are talking about 100 nanometers or 45 nanometers channel length, we are actually talking about short channel devices. Now, the dynamics of short channel devices are totally different as compared to the long channel devices. And here is the primary reason for that. Before discussing the reason, let us look at a slide where we have a comparison of the ID versus VDS characteristics as a function of VGS as well for a long channel transistor and for a short channel transistor. And then further looking at this slide, we have ID versus VGS for a long channel device and for a short channel device. Now, here we see a couple of things. There is a quadratic relationship between ID versus VGS for a long channel device. However, it is linear for a short channel device. And also, the saturation occurs way earlier in a short channel device as compared to that of a long channel device. And that is another difference. Now, the question is, why does saturation occur earlier in the short channel device as compared to a long channel device? Let me quickly try to address that. So, here is a velocity versus electric field curve for carriers, and in this curve we assume that our critical electric field is 1.5 volt per micrometer. What is electric field? Voltage divided by length. In this case, we are actually looking at the channel length. So it means that at 1.5 volt per micrometer, we are at the critical electric field and we are in the velocity saturation range. And our current would be saturated at this point. It's not going to increase any further. So now let us consider a long channel device of 1 micrometer. If we apply a voltage of 1.5 volt, then our electric field is 1.5 divided by 1.5 volt per micrometer. We are at the critical electric field point and we are into the velocity saturation region. Our current is going to be saturated for that long channel device at 1.5 volts. Now consider a short channel device of, for example, 0.1 micrometer. For 0.1 micrometer, we will arrive at the critical electric field at 0.15 volts. 0.15 divided by 0.1 turns out to be how much? Let us quickly do the calculation. 0.1. So it turns out to be 1.5 volt. So per micrometer. So once again, we are at the critical electric field at this point. So at a really low voltage, as I told you, 0.15 volt per micrometer, we are at the critical electric field right now. So it means that for the long channel device, we arrive at the critical electric field at 1.5 volts. However, for the short channel device, we arrive at the critical electric field at 0.15 volts. And that is the difference. That's why we see earlier velocity saturation and earlier saturation of currents, ID versus VDS, for short channel devices. So what I'm trying to lead to is that the dynamics of short channel devices are totally different as compared to that of the long channel devices. Okay, with that background, let us now switch to the Silvaco TCAD simulation. First, I will show you how to perform the Silvaco TCAD simulation of 45 nanometers gate length CMOS inverter, and I will run you through the code, and at the same time I have saved some figures, so it's easy to run through the code and look at the figure for reference as well. But I'm going to run the simulation for you later as well. So for this short channel device, I actually opened the long channel one, so let me go back. Okay, here is the structure. It's running from 0 to 1 micrometer in the Y direction, and it's running from 0 to 1 micrometer in the X direction. So basically, we have a 1 micrometer by 1 micrometer. And also, the built-in dimension in Z, the built-in Z dimension for these devices in Silvaco TCAD is 1 micrometer as well. So you can say it's a 1 micrometer by 1 micrometer by 1 micrometer structure. The first thing we do is meshing. So I have defined meshing in X direction and also in Y direction for the same structure. Here is the meshing. I don't want to go into the details of the meshing. Then after the meshing, my region number 1 is air, running from 0 to 1 in the X direction, and so let me keep them side by side so that we can look at the structure and at the same time we can talk about the code as well. So region number 1 is air, running from 0 to 1 in the X direction and from 0 to 0.15 micrometers in the Y direction. So this purple kind of region over here is region number 1, which is air. Okay. Now my region number 2 is actually silicon running from 0 to 1 in the x direction, this substrate region over here, and from 0.15 to 1 micrometer in the y direction. So from 0.15 to 1 micrometer in the y direction, and from 0 to 1 micrometer in the x direction. Region number 3 is silicon running from 0.5 to 0.9 micrometers in the x direction, so like from here to here, and from 0.15 to 0.65 in the y direction. So this region over here is my region number 3, and basically I have defined an envelope inside the substrate. We define an envelope for the PMOS structure. Okay. Region number 4 is once again silicon running from 0 to 0.1 micrometers in the x direction, so basically from here to here, and then from 0.15 to 0.25. So basically my region number 4 is actually the source region for the NMOS. Similarly, region number 5 is the drain region for the NMOS. Region number 6 is a thin oxide over here. You cannot see it right now, but its thickness is really small. It's just 100 nanometers. No, not even 100 nanometers. It's 5 nanometers. If you are working with short channel devices, we have to keep the thickness of the gate oxide really small in order to have lower threshold voltage for these transistors. So this is something different. Like in a long channel devices, our oxide thicknesses are generally like tens of nanometers, but in a short channel device, we have to keep this thickness really small. Okay. Then later, I have deposited this gate, an aluminum material over here as a gate. Similarly, region number 8 and 9 are actually the drain and source regions for the PMOS. Region number 10 is this thin gate oxide, once again just 5 nanometers. By reducing the gate oxide, we can further reduce the threshold voltage of the transistor. So basically, the thickness of the gate oxide gives us control over the threshold voltage. Moving further, we have aluminum. Region number 11 as is actually I've deposited aluminum as a gate metal for this PMOS transistor. Region number 12 is this oxide layer, and the purpose of this oxide is to separate the PMOS from the NMOS from the PMOS device. Then region number 13, 14 and 15, similarly moving further, region number 16. These are actually the source and drain regions. The source and drain aluminum contacts for the NMOS, and similarly the source and drain aluminum contacts for the NMOS. Similarly, in this block, I have defined the electrodes. So I will define the back side of this structure as the substrate layer. Similarly, I have defined electrode source and drain. So what I'm trying to do is, I've shown you a previous structure which resembles the CMOS inverter. In this case, what I'm trying to focus on is, I'm trying to look at the NMOS first, and then I want to look at the PMOS in order to as a proof of concept to verify the functionality of the CMOS inverter, initially for the short channel device and later for the long channel device. So basically I would define this contact as the source, this contact as the drain, and this contact as the gate for the NMOS of this CMOS inverter structure. Then I save the structure and then I start another module of Atlas, and then I call the already created structure in this module as well, and then I define dopings for different regions of this structure. Like for example, let us move forward to the doping profiles. The substrate is p-type and it has a whole concentration of 3 into 10 to the power of 18 per centimeter cube. Similarly, the N-well over here, looking at the colored chart, is N-type and its doping concentration is also 3 into 10 to the power of 18 per centimeter cube. The drain and source regions are heavily doped for the NMOS and also for the PMOS, and their doping concentrations are, this is N-type and this is P-type. Their doping concentrations are 1 into 10 to the power of 20 per centimeter cube. Now, you might think that we have already studied CMOS structures, and generally the substrate has doping concentrations of 10 to the power of 15 per centimeter cube, roughly around. It can be higher than that, it can be lower. But generally we have seen a trend that the substrate has lower doping concentrations. But that is when we are talking about long channel devices. As I already discussed, that in short channel devices, now the dynamics change. So why do we introduce higher doping concentration in short channel devices? The substrate doping concentration in short channel device is typically higher to control the threshold voltages effectively, to mitigate short channel effects such as drain induced barrier lowering and velocity saturation, to reduce the leakage currents, and to meet the performance requirements of advanced semiconductor technologies. This higher doping concentration is a critical aspect of transistor design in modern integrated circuits, ensuring the devices operate reliably and efficiently at smaller scales and higher speeds. Also, the threshold voltage of a CMOS inverter depends primarily on the doping concentrations, the physical dimensions, the gate material work functions, and the oxide thickness of the NMOS and PMOS transistors. Similarly, the switching behavior of a CMOS inverter depends primarily on its input voltage levels, threshold voltage of transistors, and its power supply voltage. After assigning the dopings, I have introduced different models. For example, bipolar, Fermi, Shockley, Red-Hall recombination, field mobility, concentration dependent mobility, OJ, optical, and print is used to look at the outputs in runtime. Similarly, I want to look at different output parameters, the band diagrams, etc. I have introduced Newton for numerical simulation of the semiconductor device. Here I have saved the structure. From that point onwards, I have introduced 3 different blocks for the Silvaco TCAD simulation of this structure. In the first block, I want to look at the ID versus VGS characteristics of this transistor. So that is the drain current versus gate to source voltage for the transistor. Now here I have set the drain voltage to 3 volts. Okay, and I'm varying the gate voltage from 0 to 3 volts at a step of 0.1, and then I plot the drain current versus gate to source voltage. Similarly, in the second block, I want to look at ID versus VDS characteristics of this structure, drain current versus drain to source voltage. So I've set the gate voltage to 3 volts, and I'm varying the drain voltage from 0 to 3 at a step of 0.1, and then I save the results. Similarly, finally, and more importantly, in a CMOS inverter, we are interested in looking at the voltage transfer characteristics of a CMOS inverter. That is output versus input voltage characteristics. So here I've set the source voltage to 0, the drain voltage to 3. So I've set the source voltage to 0 because for the NMOS the source is connected to ground. I've set the drain voltage to 3, assuming that initially the output is at 3 volts, or the output is high. And then here is the most crucial part of this code, and that is, in order to look at the voltage transfer characteristics of the CMOS inverter, we need to define the contacts as current control. And it took me some time to figure it out. In fact, I'm not the person who figured it out. A friend of mine, Amin, actually figured it out, and he gave me a hint that, hey, if you want to simulate it, if you want to simulate the CMOS inverter, if you want to look at the voltage transfer characteristics, you need to set the drain and source to current control. So that is what I've done, and this kind of resolves that issue. So I'm thankful to my buddy, Amin. I think he is from Tunisia, like he is my recent buddy, so I'm not really sure about his location, but I mean, we became friends using via the YouTube channel. So we are going to get more familiar with each other with the passage of time. But this platform over here is kind of a learning opportunity for me as well. You guys learned from me, and then you reciprocated. At times I learn from you as well, and I'm always open to learning. So then I plot these characteristics. Now let me run the simulation, and finally I quit the program. So let me run the simulation using this command. Here is the structure. Okay, I had already discussed the structure. Let me full screen it. Okay, we can look at the meshing by clicking on this icon, hit apply. Here is the meshing covering the crucial parts. Then I click on contours and then define contours, and we click on net doping. Okay. So we click on net dopings. So here are the doping profiles. The substrate has a doping of 3 into 10 to the power of 18 per centimeter cube, relatively high as compared to long channel devices in its p-type, as you can see from the color chart. but I already discussed the reason for that, why the substrate doping is relatively high. Similarly, the drain and source have n-type carrier concentration, and their dopings are 1 into 10 to the power of 20 for the NMOS. Similarly, over here we have an N-well, and the doping of this N-well is 3 into 10 to the power of 18 per centimeter cube. Similarly, the drain and source regions over here are P-type, and their carrier concentrations are 1 into 10 to the power of 18 per centimeter, 3 into 10 to the power of 18 per centimeter cube. So these are the doping profiles, and let me uncheck the doping profiles, and we can also look at the contacts by clicking on this icon. So hit apply. We have a drain contact, we have a source contact, and we have a gate contact. Okay, so this forms an NMOS. We might like to look at the electron concentration profile of the NMOS of this structure as well. So for that purpose, let me do it once again. I was kind of fast. Right click on the structure, hit display, click on these contours, go to define, and then click on contours, then okay, we click on electron concentration, and then we hit apply. Okay, so now this shows us the electron concentration profile of the entire structure under thermal equilibrium. And here, if we look at we are more interested in the channel region. So we go to tools, cut line, draw a cut line across the channel over here. Now you see the doping profile across the channel. So this is the interface of the channel close to the oxide layer, and as we see that this electron concentration of approximately 10 to the power of 6, 10 to the power of 7 per centimeter cube is really low. It's not enough. Similarly, if we look at the substrate, the carrier concentration is approximately 7, 10 to the power of 2. We can also look at the whole concentration profile at the channel under thermal equilibrium. So let us do that. Okay, here is the whole concentration. We know this substrate is p-type with a carrier concentration of 3 into 10 to the power of 18 per centimeter cube. I zoomed in on that and it's verified. Now you know that if the whole concentration in the substrate is 3 10 to the power of 18, what should be the electron concentration? Or roughly, if the whole concentration is 10 to the power of 18, what should be the whole concentration? We have a really simple formula for that. N times P is equal to Ni square, or the product of the electron concentration and the whole concentration is equal to the intrinsic carrier concentration square. What is the intrinsic carrier concentration of silicon? Approximately 10 to the power of 10. So 10 to the power of 10 square is equal to 10 to the power of 20. If the whole concentration is 10 to the power of 18, the electron concentration should be 10 to the power of 2. Similarly, if the whole concentration is 10 to the power of 6, the electron concentration should be 10 to the power of, similarly, if the electron concentration is 10 to the power of 6, the whole concentration should be 10 to the power of 14. But anyhow, inside the channel, we need a high concentration of electron to connect the drain with the source. And at this point, under thermal equilibrium, our electron concentration, represented by the red curve, is really low. Now, what happens under an applied voltage? So in this case, we are looking at the ID versus VGS characteristics of this structure. And as we can see that the threshold voltage of this structure is approximately 0.5 volts. We can further reduce this threshold voltage by further increasing the doping concentrations and by reducing the gate oxide thickness. We have control over that. Similarly, we have the ID versus VDS characteristics are also simulated at this point. So we want to look at drain current versus drain voltage, hit apply, and here is ID versus VDS characteristics. The saturation point is approximately 0.4 volts, and you can see the curve. Similarly, this is the structure for the ID versus VDS characteristics. So we can look at the electron concentration profile for this curve as well. Hit apply. Okay. Okay. So now here is our channel. Now you see from the profiles we have more electron concentration under biasing. And to verify that, we can draw a cut line once again across these regions. And now you see that, let us check the whole concentration as well. Hit apply. So now you see that as compared to the thermal equilibrium condition, here is the thermal equilibrium condition where the electron concentration was 10 to the power of 6. When we apply high voltage across the gate, now the electron concentration has increased to 10 to the power of 19 per centimeter cube at the channel. So now we have connected the drain to the source. And now finally, we are simulating the ID versus VD versus VGS characteristics, or we are simulating the voltage transfer characteristics of this structure right now. So it's gonna go up to 3 volts. Right now it's at 1.4 volt. It's gonna take a little bit of time. Let's wait for that. While it's simulating, I'm going to head out for a second. I'm going to be back. We are almost there. Okay, we want to look at VD versus VGS characteristics of this structure. So here is the drain voltage versus gate voltage, or you can say output versus input voltage, or you can say voltage transfer characteristic of the inverter. As we know that we started for the drain voltage, we started from a high voltage. So when the gate voltage is low, the drain voltage was high. When we kept increasing the gate voltage, then the drain voltage switched or transitioned from high to low, and that is the basic functionality of the CMOS inverter. So like in this structure, we can also display potentials. We go to contour and we hit on potential, we hit apply. Okay, so the gate voltage is now high, and we have connected the source where we have made a channel. We created a channel connecting the drain with the source, and when the input is high, the drain is connected to the source, so the output is going to switch from high to low. So this functionality of the CMOS inverter is verified now with this code. I've also created codes for the PMOS part of the short channel device, as you can see over here, but its simulation is going to take this is for the long channel. I have it for the short channel device as well. Okay, so this is for the short channel device. I've written codes for all of them. NMOS 45 nanometers, PMOS 45 nanometers, PMOS 1 micrometer, NMOS 1 micrometer. Similarly, other codes like 1 micrometer CMOS, etc. But now that we have seen the functionality of the CMOS inverter, I'm not going to run the simulation for each and every one of them. For example, here are the results for PMOS 45 nanometers, ID, VD versus VGS. So instead of running the simulations, once again, we are just going to look at the results. We already discussed this part. Here is the whole concentration of this entire structure. And as you can see, under thermal equilibrium, the whole concentration is super low inside the channel for the PMOS. Here is the energy band diagram of the metal oxide semiconductor structure. Here is the metal, here is the oxide. This is super thin, so you cannot really see the wide band gap of the oxide, but this band gap of the oxide is approximately 9 electron volts, and then we have the semiconductor or the substrate part. Here is the ID versus VGS characteristics for the PMOS. In PMOS, everything is negative, drain current, gate voltage, etc. You can see the turn-on point for the PMOS. Then here is the whole concentration under biasing. When we apply low voltage to the gate for a PMOS, it's going to attract holes, forming the channel, connecting the drain with the source. So now we see the whole concentration is 10 to the power of 19, pretty high as compared to the thermal equilibrium one. Here is the whole concentration profile under biasing. Now you see that the drain is connected with the source. Here is the metal oxide semiconductor structure under biasing. ID versus VDS characteristics, where we see like kind of saturation over here at this point around 0.5. Here is the voltage transfer characteristics. Quickly I'm going to run you through the the results for the 1 micrometer long channel device as well for the NMOS and then for the PMOS. Here is the structure. As you can see that this is long channel 1 micrometer device. Here are the doping profiles under thermal equilibrium, the electron concentration at the NMOS channel, the electron concentration profile for the entire structure, the metal oxide semiconductor energy band diagram, ID versus VGS for the 1 micrometer device. Here is the structure under biasing, like we have applied a high voltage to this gate, attracting electrons, forming the channel, connecting the drain with the source. Here is the electron concentration inside the same channel under biasing, which is now high as compared to thermal equilibrium. Here is the ID versus VDS characteristic curve. The drain voltage versus gate voltage, voltage transfer characteristics not as good as compared to that of the short channel device. We can further optimize this, and here is the potential across the structure under biasing. I wanted to mention one point. So here is the doping profile of the long channel device. In this case, the substrate doping is 5 into 10 to the power of 15 per centimeter cube. Similarly, the N-well also has a doping of 5 10 to the power of 15 per centimeter cube, much lower as compared to the short channel substrate doping. And similarly, I have simulated the PMOS for the long channel device as well. As you can see, source, gate, and drain. Doping profiles, hole concentration under thermal equilibrium, profile of the hole concentration, the metal oxide semiconductor energy band diagram under thermal equilibrium, ID versus VGS. Now this is the hole concentration profile under biasing, connecting the drain with the source for the PMOS. Here is the hole concentration under biasing, pretty high at the channel. Here is the metal oxide semiconductor energy band diagram under biasing. Drain current versus drain voltage, voltage transfer characteristics, and the potential across the entire structure. So basically it was kind of my first attempt working on the CMOS inverter, and I think these are decent results covering current versus voltage and voltage transfer characteristic curves for the CMOS inverter. I hope you like this work, and I hope that you learn from it, and maybe you might give me a couple of hints on further improvement of my codes and these device simulations as well. We live in a scientific community, and in a scientific community we should always be open to learning from each other, and that is my passion. I would try to live up to my passion and reputation. With that, I'm going to say goodbye. Take care. Adios.